Hello everybody, I welcome you all to NCAS Geology class. In previous class, I have discussed about the symmetry operations which involve reflection, rotation, translation and inversion. Now, I will discuss on the compound operation which involves joint operation of rotation with inversion, translation with rotation and glide operation. So all those things I will now discuss. These are broadly classified into glide reflection, roto-inversion and screw rotation. Now let us start glide reflection. Here there will be sliding and there will be reflection. It combines translation parallel to the mirror plane with reflection across the mirror plane to produce the glide plane. Let us say this is the unit cell. This is the unit cell, and this unit cell has been arranged in a symmetrical order to produce a row of unit cells as presented here. Now we can operate the glide along with reflection. How it will take place? So the atom here slides up to this place, then reflects to this side, slides up to this place, reflects about to this side, slides up to this place, reflects up to this side. So sliding, reflection, sliding, reflection, sliding and reflection, sliding and reflection. In this manner, if we see that the atoms are arranged and they are correlated, then we can say that these atoms, they are related to each other through gliding and reflection. So this is a case when we talk about in 2 dimension. In 3 dimension, that will give rise to space lattice. Here the glide plane operation has been shown in 3 dimension. These are the 3 atoms oriented, they slided up to this place, then reflected, slided up to this place and reflected, slided up to this place and got reflected. So this type of arrangements are being seen, then they can be the atoms arranged in 3 dimension, and that arrangement is seen, then it is called the glide plane operation in 3 dimension. So this figure 1a shows one unit cell with 3 atoms. In it, no glide plane symmetry is apparent. But in figure B, there are a row of unit cells. In it, some sort of symmetry in form of a dashed line is apparent here. So with respect to this line, there is symmetrical arrangement of atoms on both sides. If you correlate them in figure C, it has been shown that there is a translation followed by reflection. First the atoms glide up to half the length of the unit cell, then reflects over the plane, then it glides half the length of the unit cell, and after that it reflects. In this manner the atomic structure has been developed as shown in figure C. So this is the mirror, gliding, reflection, gliding, reflection. In this manner, this arrangement has been shown for the atoms In figure D, there is a glide in 3 dimensions. It shows a triangular group of atoms repeating in zigzagging manner back and forth from one side to the other of the glide plane. There are 6 types of glide planes, and it may involve translation parallel to A axis or B axis or C axis, and for crystals of cubic and tetragonal system, the translation may be diagonal, one from one corner of the unit cell to the other. So translation may involve along A axis, B axis, C axis, and diagonally from one corner to the other corner of the unit cell. The letters A, B, C, N and D symbolize these glide planes. That has been shown here in the tabular form. Operation is M with a mirror plane, proper mirror. It involves no translation. So, no translation in that, there is simply reflection over a plane. If it is a glide across A, so it is axial glide parallel to A, and it has the atoms have moved half of the length of the unit cell along A. It is B axial glide, and the glide has taken place parallel to B, and it has covered half of the distance of B. Axial glide parallel to C has gone half of C. In diagonal glide, which is called as N, it is parallel to the face diagonal, it is denoted as half T. And in diamond glide D, it is parallel to main diagonal, it is 1 by 4 T. The translation is about 1 by 4 T. So, these are the 5 types of glides along with mirror that are seen in atomic arrangement. So, that has been explained here. The atom is here, it glides half of A, reflects over to this side, glides half of A, reflects to this side. So, this is the mirror plane across which the reflection has taken place. So, this type of arrangement can be correlated with glide and reflection, glide and reflection. So, the above, so this is the type of glide planes involving translation and reflection. So, this is all about how the atoms are arranged along with glide and reflection. The glides may take place along A axis, along B axis, along C axis, along face diagonal, along body diagonal. Then let us discuss how the atoms are arranged through rotoinversion. It involves rotation about an axis with inversion through the center in order to produce a rotoinversion axis. These are 1 bar, 2 bar, 3 bar, 4 bar, 6 bar. These are the rotoinversion axes. They are articulated as bar 1, bar 2, bar 3, bar 4, bar 6. In rotoinversion operation, rotation and inversion are applied simultaneously. For example, if you talk about 4 bar rotoinversion axis, what happens? Let us imagine a solid dot, a point above the page. Let us say this is the third. It rotates 90 degree, and inverts to produce the dot point below the page. So, it goes down and produces a open dot below the page. Then this is 90 rotation. Then as it is a fourfold axis, there will be 4 rotations at 90 degree interval. So, in next 90 degree interval, the face occurring at the bottom of the page rotates 90 degree, and comes up as a solid dot in the upper page. A dot point below the page rotates 90 degree inwards to form the solid dot above the page. Same thing, this rotates 90 degree inwards and produces a dot at the bottom page. Solid dot rotates 90 degree inwards to form the open dot below the page. Then it rotates 90 degree and produces the dot below the page, or solid dot above the page. So we see that the operation is involving rotation along with inversion through the center. So here the rotation of 360 degree causes 4 dots to be produced. 1, 3 are the open dots. This is 1, this is 3 open dot, 2 and 4 are solid dots above the page. All are related by 4 bar roto inversion operation. That has been shown here. These are the open dots below the page. These are the solid dots above the page. If you take into account, this is one face, this is one face, this is one face, this is another face. If you rotate it, this type of operation will be seen. If you rotate 90 degree, then below this page the face will appear. Again rotated 90 degree, above this page will appear. Then rotate 90 degree, below this page will appear. In this manner 4 dots will appear, or if the solid is having this type of these are the 2 solid dots for the upper hemisphere, these are the 2 solid dots for the lower hemisphere. They are related to each other with respect to 4 bar rotation axis. It is represented by a symbol like this, a symbol like this, 4 bar rotation axis. Then let us see how a 2 bar axis operates. It is equivalent to M or mirror plane. Let us see. The solid dot above the page rotates 180 degree and inverts through the center to form a open dot below the page. Again rotates 180 degree to form a solid dot above the page. So solid dot, open dot, this is open dot below the page. They lie one above the other. Both solid and open dot, they lie one above the other as if a mirror plane is horizontally present between them, so that one is the mirror image of the other. If we project both, this will be here, this will be here. So that thing has been shown here. So one is lying above the other as if there is a mirror plane between these two. One is on the upper hemisphere, the other is at the lower hemisphere. They are represented by the horizontal plane. So this is equivalent to M, mirror plane. 2 bar is equivalent to mirror plane. 4 bar is equivalent to simply 4 bar. And when you talk about 3 bar, this is equivalent to 3-fold axis with an inversion center applied separately. And 6 bar is equivalent to 3 by M. 3 bar, this type of This is 3 bar. We see the threefold axis. If you rotate at 180 degree, 120 degree interval, each face will come to same position. So this axis will be axis of threefold symmetry, and below it there will be three axes. Three faces are there on the top. This is one face, this is another face, and this is another face. Three are on the upper hemisphere. Similarly, three at the lower hemisphere. There is third face on the back side. So they are just one above the other. That's why by m is there. So 3 bar operation is equivalent to 3 by m. Rotation by 180 degree, inversion. Rotation by 180 degree, then inversion. Rotation by 180 degree, then inversion. So we will get three faces. We will get three faces on the bottom, three faces on the top. One will be lying above the other. That's why mirror plane exists. So 3 bar operation is equivalent to 3 plus I. Similarly, 6 bar operation will be equivalent to 6 bar is equivalent to 3 by m, because axis will rotate 60 degree, invert will appear here. Rotate 60 degree, will appear here. Rotate 60 degree, will appear here. So these are the 3 points where there will be lower hemisphere, open dot at the upper hemisphere. So it will be equivalent to 3 by m. So 6 bar is equivalent to 3 by m. 3 bar is equivalent to 3 plus I. 2 bar is equivalent to m. Then now let us discuss what is screw axis. Screw rotation. It involves along with translation. It is a symmetry operation that combines translation parallel to an axis with rotation about the axis. 2 1 3 1 3 2 4 1 4 2 4 3 6 1 6 2 6 3 6 4 6 5 are the screw axis. So what is 2 1? What is 3 1? Let us discuss. So 2 means it is axis of twofold, axis of twofold symmetry. Twofold symmetry. But 2 1 means there will be rotation by 180 degree, then translation. Translation of half of the unit cell length, then rotation 90 degree, translation half, rotation 90 degree, translation half, like this. So let us say what is 4 1 screw axis. Here the unit cell edge has a length t. 4 1 screw axis involves rotation of 90 degree and translation of t by 4 distance. Let us say point A. Point A rotates 90 degree, and is transmitted t by 4 unit to this position, to A1 position. This is A1 position. Then from A1 position rotates 90 degree and translates t by 4 to point A2 location. Then A3 location, t by 4 transmits. Then T4 of location. So we see that along the unit length we have the axis of translation involving 4 operation. So this was here, rotates 90 degree and appears here, then rotates 90 degree and appears here, then rotates 90 degree, appears here, then rotates 90 degree, appears here. So within the unit cell length we have this one, this one, this one, and this one. These are the, if this is the atomic arrangement, we can say it is showing 4-1 atomic arrangement. That has been shown here. That has been shown here. Goes to this place, then this place, then this place, then this place. So this is one unit cell. This is one unit cell. So this cell has been repeated. If this is the type of atomic arrangement, this will be called as 4-1. If we say it is 4-3, then what happens? The unit length is, or the T is the unit cell length. So there will be rotation by 90 degree, to 3/4 of T, because 4-3, it is 4-3. So it will rotate 3/4 of T and it will appear here. Then it will rotate 3/4, it will 6/4, it will appear here. Then rotates 9/4, it appears here. Then 12/4, it appears here. So what happens? We see that the total length of 3 unit cells is being covered, and this has been compressed. This can be compressed to be equivalent with this T1 with 4-1. If the 3 unit cell will be compressed to 1 unit cell, then the atoms will come closer and it will resemble to 4-1. So 4-1 is equivalent to 4-3. It is said that 4-1 is equivalent to 4-3. So the 4-3, how it shows? It shows a length equal to 3 unit cells length. It presents points in different locations. This is impossible because all unit cells are to be identical. The unit cells can only be identical while also being consistent with a 4-3 axis, and it will be possible by adding extra points to the points as shown in the figure. Extra points will have to be added. That has been added here. It has original position of 3/4, and these are the additions. These are the additions. These are the additions. This was not there, so these are the additions. This one, this one, this one. These are additions, so that the unit cell gets completed by compressing all those atoms within one unit cell. We get this structure, which is a, we can say it is equivalent to this 4-1 type, right? Equivalent to 4-1 type, only same thing appears to be the mirror of the other. Figure A, B, C, they are showing 4-3 screw axis, and this is 4-3 screw axis A, B, C. These are 4-3 screw axis, and they have been compressed to it's impossible because 3 unit cells, it involves the operation of 3 unit cells. If we take the translation of 3/4 unit with 90 rotation, it will cover 3 unit cells length. So these gap portions will have to be represented by atoms, so that the cell will represent the 4-1 will be equivalent to that of the 4-1 type of atomic arrangement. In figure 16a, C show same result. A and C, they show same result. That is, unit cells can only be identical while also being consistent with the 4-3 axis by adding extra points as shown in figure 17a and b. Extra points have been added here. These were the original. So, if we compare 17b and 17c, B and C, 4-1 axis is the mirror image of 4-3 axis. They form the enantiomorphic pair, sometimes called right-handed and left-handed skew axis. So, 4-1 axis is equivalent to 4-3 axis. When all combinations are considered, there are 20 possible rotation axes such as 1, 1 bar, 2, 2, 1, 3, 3, 1, 3, 2, 3 bar, 4, 4, 1, 4, 2, 4, 3, 4 bar, 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6 bar. So, these are the 20 rotation axes involving translation and rotation. So, these are the, we can say, this is the screw axis, this is screw axis, screw axis, these are the screw axis, screw axis, screw axis, these are screw axis which involve translation and rotation. Others are, these are the rotor inversion, this is the only inversion, and these are direct axis of rotation. 4 bars, 1 bar, the rotor inversion axis, 1, 2, 3, these are the simple axis of 1-fold, 2-fold, 3-fold rotation. So, 2-1, it involves translation of T by T 2 unit and rotation of 180 degree. This is 180 degree, 2-1. 3-1, it involves translation of T by 3 unit and rotation of 120 degree. 4-1, it involves translation of T by 4 unit and rotation of 90 degree. 6-1, it involves translation of T by 6 unit and rotation of 60 degree. 4-2, it involves rotation of 2 by 4 T and rotation of 90 degree. 4-3, it involves rotation of 3 T by 4 and rotation of 90 degree, where T is the unit cell edge length. So, in this manner, if the atoms are arranged, then they are considered to be the screw axis. This is the screw axis for 4-3, this is 4-1. They appear to be the mirror image of each other. Here appear to be, here this is, here this one, here this is, here this one, here this is, here this one. So, they just appear mirror image of each other. So, 4-1 is equivalent to 4-3. So, 4-3 means there will be translation of 3 by 4 unit and rotation by 90 degree. Then translation 3 by 4 unit and rotation by 90 degree. In this manner, if the atoms are arranged in the unit cell, then that axis can be called as the 4-3 screw axis. Similarly, 4-1, similarly 6-1. In case of 6-1, the rotation will be 60 degree, translation will be T by 6 unit. Then 60 degree, translation will be T by 6 unit, like this. So, if this type of arrangement is shown in atoms, then that axis will be called as 6-1 axis. So 6-1, 6-2, 6-3, 6-4, 6-5 are the rotation axis involving 6-fold rotation axis. 4-1, 4-2, 4-3 they are involving axis of 4-fold rotation. Similarly 3-1, 3-2 that involves axis of 3-fold rotation. 2-1 involves axis of 2-fold rotation, and others are simply axis of rotation 1-fold, 2-fold, 3-fold, 4-fold, 6-fold, and 1 bar, 2 bar, 3 bar, 4 bar, 6 bar. So this is all about the screw axis. So the atoms that we see in the crystals, they conform to these 20 types of symmetry operations involving rotation, and there are 5 types of operation involving reflection along with translation: A, B, C, N and M. So these operations, they account for the crystal structure of all the crystals, and accordingly the crystal structure develops in almost all the crystals. If we take into account the 4-3-4-2 screw axis, the subscript 2 indicates translation of 2 by 4 T unit for every rotation 90 degree. So it involves 360 rotation to complete the screw axis, and thus it covers T by 4, 2 by 40, 2 by 40, 2 by 40, 2 by 40, or it covers 2 T translation, twice the unit cell edge length is covered to accommodate 4T screw axis. As the unit cells are to be identical, all points of 4-2 must be represented within 1 unit cell length, and therefore extra lattice points are to be added. Hence 4-2 axis requires the presence of a 2-fold axis. If we compress it, 4-2 becomes equivalent to a 2-fold axis. This is 2-1 and this is 4-2. So it takes 2 unit cells. When that has been compressed, this comes over here, this comes over here, this comes over here. So we get as if it is an axis of 2-fold symmetry, having east to west, north south, like this. So it involves it requires the presence of a 2-fold axis, 4-2. So here in the tabular form, the 20 possible space symmetry operators have been shown. 1, it is involving no translation, it is 1-fold axis. 1 bar, it is inversion center, no translation. 2, 2-fold axis, no translation, 180 rotation. 2-1, it involves 180 rotation and half T translation. 3, rotation 120 degree and no translation. 3-1, it is a screw axis, rotation 1 by 3 unit of T. 3-2, it involves 2 by 3 of 2T. 3 bar, it is rotor inversion axis involving no translation, and 4-fold axis, no translation. 4-1 involves translation of T by 4 unit. 4-2 involves 2T by 4 unit or half T unit. 4-3, it involves 3 by 4 T translation. 4 bar, no translation, it is 4-fold rotor inversion axis. 6-fold rotor inversion axis, no translation. 6-1 involves 1 by 6 translation. 6-2 involves 2 by 6 translation. 6-3 involves 3 by 6 translation. 6-4 it involves 4 by 6 translation. 6-5 it involves 5 by 6 translation. 6 bar it involves no translation, it is equivalent to 3 by n. So, these are the 20 possible symmetry operations involving rotation along with translation. So, this is all about the operation of rotation, operation of translation, operation of glide planes, operation of reflection, operation of inversion, to which the atomic structure of crystals conforms, as a result of which all the 32 classes of symmetry or 230 space groups of crystals are being produced, which all include these 20 symmetry operation involving axis of rotation along with translation and 5 operations involving reflection with translation. In my next video, I will discuss about the two-dimensional motifs in lattices and how they give rise to 17 types of plane space groups. Thank you all giving a patient hearing to my talk.